This content is produced by PASS, the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. The central field principle is an unbroken load path. I can have good lumber, correct panels, and a clean-looking wall, but the lateral system only works as intended when every required connection carries force into the next connection. Wind pushes on the building. Earthquake motion moves the foundation under the building. Roof and floor assemblies collect those sideways forces. The walls carry them downward, and the foundation receives them. A missing link does not merely make one detail look unfinished. It interrupts the force transfer that the approved design depends on. That is why my first supervisory question is not, does the wall look solid? My question is, can I trace the load from the diaphragm, through the wall, through the sill and anchorage, and into the foundation without guessing about a connection? That question keeps the contractor in the correct lane. I am not redesigning the structure. I am verifying that the installed work matches the approved plans, schedules, and required hardware. A roof or floor diaphragm acts like a broad horizontal collector. It gathers lateral force and delivers that force to vertical resisting elements. Those vertical elements may be prescriptive braced wall panels or engineered shear walls. From there, the force continues through the wall sheathing, edge fasteners, framing, sill connection, anchor bolts, hold downs where specified, and finally into the foundation. There are two force directions I want to keep separate. Shear tries to slide the wall along its base. Overturning tries to lift one end while pushing the other end down, like a tall cabinet being tipped. Anchor bolts and sill connections help resist sliding. Hold downs at wall ends resist the uplift side of overturning. One does not casually replace the other because they are handling different actions. I put the load path into a sequence chart because the order matters. I start at the roof or floor diaphragm, move into the vertical wall system, follow the sheathing and framing to the base, and then separate the sliding connection from the overturning connection before both reach the foundation. The chart is not a design detail, it is a field check sequence. Suppose a crew installs every hold down but leaves a required horizontal sheathing seam floating between studs with no solid backing. The hardware at the bottom may be correct, but the panel edge cannot transfer force through the prescribed fastener line into framing or blocking. The path is interrupted above the hardware. The practical lesson is simple. Expensive hardware cannot repair a missing connection somewhere else in the chain. A braced wall panel and an engineered shear wall solve a similar problem, but I do not treat the terms as interchangeable. A braced wall panel belongs to a prescriptive braced wall system under the California Residential Code. The code supplies standardized layout rules for qualifying residential construction. An engineered shear wall follows calculated details under the California Building Code and the approved structural plans. For a prescriptive braced wall line, a panel must begin within 10 feet of each end of the designated line, and the distance between adjacent panel edges must not exceed 20 feet. Those are placement checks for that prescriptive system. I do not carry those numbers over and use them to relocate an engineered shear wall. Engineered wall locations, panel lengths, cords, hold downs, sheathing, and fastening come from the approved design. The comparison chart separates the two systems. On the braced wall side, I show the prescriptive framework and the 10-foot and 20-foot placement rules. On the engineered shear wall side, I show plan-specific locations, fastening, and hardware. The contractor boundary is the same in both columns. Build what is approved, identify conflicts early, and send design changes back to the responsible design professional and approving authority. Imagine a contractor who finds a plumbing conflict at the end of an engineered shear wall. Sliding the wall 2 feet down the line may look harmless in the field, but that move changes the location of the resisting element and may change the load path. The correct supervision move is to stop the affected work, document the conflict, and obtain an approved resolution. I do not redesign around the conflict with job site instinct. Panel edges deserve close attention because a shear wall is not just a field of plywood or oriented strand board. Its capacity depends on the sheathing transferring load through specified fasteners into framing. In California, seismic force-resisting systems, unblocked shear walls are prohibited. Horizontal and vertical panel edges must occur over framing or solid blocking and be fastened there as required. The easiest defect to miss is a seam that looks neat from the face but has no backing behind it. Before concealment, I check the other side or verify blocking as framing proceeds. Once finishes cover the wall, proving that hidden blocking exists becomes slower, more expensive, and sometimes destructive. California also prohibits staples as fasteners for wood structural panel shear walls and diaphragms. A panel manufacturer may list staples for some uses, but that does not override the California prohibition for this structural application. I verify the nail type, length, diameter, and spacing against the approved shear schedule. I do not accept a fastener substitution because the gun is already loaded, or because the crew used it on another project. The reference chart groups the field checks that belong together. Every panel edge backed, every joint fastened to framing or solid blocking, no staples for the structural shear wall or diaphragm fastening, and the special high shear conditions that call for wider framing and staggered nailing. It is meant to be used like a compact pre-inspection checklist, not as a substitute for the approved schedule. A common shortcut is to add extra nails after discovering a wrong fastener pattern. More is not automatically better. Nails driven too close to an edge, too close together, or into split framing may reduce the quality of the connection. The right correction depends on the approved details and the current condition of the wood. I pause, inspect the damage, and obtain direction when the repair is not already covered by an approved detail. High-capacity panel joints are where fastener density and wood behavior collide. When the shear design value exceeds 350 pounds per linear foot in Seismic Design Categories D, E, or F, adjoining panel edges require framing that is 3 inches nominal or wider, or 2 2x-members fastened together as permitted by the approved design. When that wider framing is required, the joint nailing and sill plate nailing at panel edges must be staggered. The reason is practical and visible. A dense straight line of large nails driven into a narrow member can place repeated wedges along the same grain line. The member may split, and a split member does not provide the intended fastening base. Wider framing creates room for the fasteners, and the staggered pattern keeps them from stacking on one grain line. I want to be precise about the phrase 3 inches nominal. It does not mean I take a tape and demand an actual 3-inch finished width from every piece. Nominal lumber language refers to the standard size designation. The approved detail may call for a solid 3x-member, a larger member, or 2 2x-members fastened together. I verify the exact assembly shown rather than inventing my own version of double framing. Suppose the shear schedule calls for tight edge spacing beside a large garage opening, but the panel joint lands on a single standard stud. I do not let the crew keep nailing until the stud splits. I catch the conflict before sheathing, compare the framing to the schedule, and rebuild the joint as detailed. That is less dramatic than a repair after inspection, and it protects the connection the engineer actually designed. At the foundation, I separate sliding resistance from overturning resistance again. Anchor bolts clamp the sill connection to the concrete and participate in transferring shear. Hold downs connect the end cords of the wall to anchors intended to resist uplift from overturning. The wall needs the specified pieces in the specified places. Adding more anchor bolts does not erase a required hold down, and a hold down does not replace the sill anchorage shown on the plans. In Seismic Design Categories D0, D1, and D2, the California Residential Code requires plate washers at foundation sill anchor bolts that are not less than 0.2 9-inch thick by 3 inches by 3 inches. The plate washer goes between the sill plate and the nut. If the plate washer has a diagonally slotted hole, a standard cut washer is placed between that plate washer and the nut. The hardware chart compares anchor bolts, plate washers, hold downs, and wall end cords by function and field check. I use it to stop a common mix-up. Anchor bolts and plate washers address the sill connection and sliding force transfer. Hold downs and their connected cords address wall end uplift. The approved plans control the model, post or cord size, fastener count, anchor type, and embedment. The plate washer dimensions are worth memorizing, but I do not let memorization replace inspection. I still check that the washer is present, flat, properly located under the nut, and compatible with the hole configuration. I also check for damaged threads, missing nuts, oversized wood holes, and hardware that does not match the planned callout. A correct part installed incorrectly is still a field problem. My pre-inspection walk starts with the plans in hand, not from memory. I confirm wall locations and lengths, then panel thickness where shown. I verify every horizontal and vertical edge has framing or solid blocking. I compare the fastener type and pattern to the schedule, paying special attention to boundary edges, panel joints, top and bottom plates, and any tight spacing that requires staggered rows. Then I look at the framing behind the fasteners. I check for split studs, missed framing, and unauthorized substitutions. At high shear joints, I confirm the required wider member or approved double member assembly. At the wall ends, I trace the cord into the hold down and the hold down into its anchor. At the base, I verify sill anchorage and the required plate washers. I also coordinate other trades. If a plumbing route conflicts with a shear wall location, wall end cord, hold down, or required blocking, I stop the affected work and obtain an approved resolution. I do not tell a crew to move structural hardware or shift the wall around the conflict. This is where sequencing saves money. I want blocking, straps, clips, hold downs, and anchors visible before insulation, utilities, or finishes make them hard to inspect. I want conflicts resolved before a concrete pour locks anchors in place or before sheathing hides framing. Inspection readiness is not cosmetic cleanup. It is the ability to show that the concealed load path has been built as approved. A useful mental check is to ask 3 questions at each connection. What force arrives here? What part receives it? What carries it next? If any answer is unclear, I stop tracing and compare the work to the plans. That keeps the inspection focused without pretending that I am performing engineering calculations. Structural supervision does not excuse unsafe framing methods. Effective July 1, 2025, employees doing residential type framing work must have conventional fall protection when they are 6 feet or more above the lower level. The covered work includes activities such as walking top plates, installing joists, setting trusses, and placing sheathing. The old 15-foot residential framing threshold is no longer the current rule. That matters because experienced field habit can be stronger than a recent regulation. A worker on a 9-foot top plate is above the current 6-foot trigger, even though that height would have fallen below the old threshold. The timeline chart makes the transition unmistakable. It shows the former 15-foot threshold, the July 1st, 2025 effective date, and the current 6-foot trigger for residential type framing. I also note that a fall protection plan may replace conventional methods only when the employer can demonstrate that conventional protection is infeasible or creates a greater hazard. Conventional protection can include scaffolds, guardrails, safety nets, or personal fall arrest systems, depending on the operation and the compliance setup. I do not treat a safety monitor or controlled area as an automatic convenience option. The employer carries the burden of the required demonstration before using the alternative plan. On a truss setting day, my structural checklist and safety checklist run together. I verify the walls and bracing are ready for the operation, and I verify the crew has a compliant fall protection method before anyone works at or above the trigger height. Stopping the crane after workers are already on the top plate is late. The better supervisory decision happens during planning. I want the full lesson reduced to a few connected decisions. First, trace an unbroken load path from diaphragm to wall to foundation. Second, keep prescriptive braced wall placement separate from engineered shear wall details. Third, require solid backing at every panel edge and reject staples for wood structural panel shear wall and diaphragm fastening. Fourth, When the high shear condition applies, verify 3-inch nominal framing or the approved double member option and stagger the required nailing. Fifth, separate sill anchorage from hold-down uplift resistance. Sixth, use the current 6-foot fall protection trigger for residential framing work. These are testable concepts based on the published CSLB study outline, but the practical value is larger than memorizing isolated terms. Each item is a link in either the structural load path or the supervision path. The approved plans tell me what to build. The field walk tells me whether it was built. The inspection sequence tells me when to catch it. The safety rule tells me how the crew may perform the work. There is an audio practice quiz for this specific episode on shear walls, braced wall panels, and lateral resistance. It is audio-based. The questions are read aloud and you answer by tapping, because I know you may be studying while driving, working, or moving between jobs. Go to the description below this video. You will see a link that says, Pass the CSLB. Tap it. It will take you straight there. Comment below with any questions about the framing details or safety rules I covered. Subscribe so I can help you stay on track through every episode until you get your license. I am rooting for you, and I want the next study session to feel just as practical as this one.